Today we're going to begin our unit on integrals. And before we actually get into what an integral is and what it's useful for, we're just going to take a look at a couple of quick and basic situations here. So the first one is we've got a car traveling at 60 miles an hour, exactly 60 miles an hour for 2 hours, t equals 0 to t equals 2. And so we're going to graph the velocity function. So that should be really easy to do. If this is 60, and here's t equals 1, and t equals 2, if the velocity is 60 the entire time, it would look like that would be our function right there. And if I asked you how far the car traveled during the first 2 hours or during those 2 hours, we'd just say, well, if it was going 60 miles each hour for 2 hours, that'd be 60 times 2, which would give us 120 miles. Should be pretty straightforward. No, this is not integrals yet. This is just easy stuff getting us down the road to why we need integrals. Now I'm driving along, and this time I'm driving along in my very magic car. I'm traveling at exactly 60 miles an hour for an hour. And then at t equals 1, somehow I snap my fingers and my magic car jumps up and starts going exactly 70 miles an hour. There's no gap there in the time it takes. It just instantaneously changes. I'm going to make this thing not a function by saying I was going 60 miles an hour and 70 miles an hour at t equals 1. An instantaneous change there. Obviously not possible in real life, but for our purposes, we're going to use that idea. So if I went 60 miles an hour for an hour, that ought to be 60 miles. And then if I went 70 miles an hour for an hour, that ought to be 70 miles, meaning we would have gone a total of 130 miles in this situation. Another easy one, just getting us ready to think about what integrals mean. And one more real simple, easy one. Now I've got a car that's really good at accelerating at a constant rate. So I'm going to start at 60 miles an hour, and I'm going to finish at 70 miles an hour after exactly 2 hours. And I'm not going to have any change in my acceleration. My velocity is going to increase at a constant rate. So that's supposed to have be a linear piece of my function here from t equals 0 to t equals 2. And so now the question is, how far did I travel during those 2 hours? Well, we'd have to think about, since we're accelerating at a constant rate, it should be easy enough to find our average velocity. Our average velocity would be 60 plus 70, and then divided by 2, which would give us 130 over 2 is 65. And then we'd have to take that 65 and multiply it by the number of hours that we averaged that, which would give us 130 miles. And with any luck, as we went through this process, we might have noted each time that the distance that we traveled, and we're going to go back to that first slide, the distance that we traveled here was 120 miles. Well, if I were to just drop a vertical line straight down from my endpoint, and we would look at this rectangle that we've got underneath the curve, and if I tried to find the area of that rectangle, well, that would be 2 units times 60 units here. And that'd be the 60 times the 2 that we did. And if we think about multiplying those, the first one, the velocity, is in miles per hour. And the other one is just in hours. So we're multiplying miles per hour by hours, which should allow us to cancel out those units of hours, leaving us with just miles. So it makes sense that if we found the area underneath this velocity curve on a time and velocity axis, we should get the total distance that we traveled. And if we look up here at the second one and did the exact same thing, let's say I just turned this into a couple of little rectangles here. The first one is 1 unit by 60. So this one was 60, and that's how we got our 60 here. And our other was also 1 unit by 70. That's how we got the 70. And the area underneath that graph, once again, came out to be the total distance that we traveled. And same thing here. This one, if we drop a straight line down here, this is just a trapezoid if you think about it, a trapezoid lying across its height, right? This would be the height of my trapezoid, and this would be base 1, and this would be base 2. And, well, how do you find an area of a trapezoid? Well, you do the average of the bases, base 1 plus base 2 divided by 2. That's that 65. And then you multiply it by the height, which was 2, and it gave us 130 miles, which was the area of that trapezoid that we get underneath that curve. So we can see that there are some cases, some instances where it's useful to know what the area underneath a curve might actually be. Now, these were all really simple, really straightforward functions where it's really easy to find the area under the curve. But that won't always be the case. So here I'm looking at the car traveling at a rate that varies from t equals 0 to t equals 2. And it's got a velocity that's given by this, well, fluctuating graph. It starts at 60, goes up, goes down, back up and down and up and down. And I don't know, somewhere around 60 miles an hour again after 2 hours. So we know that the total distance that we traveled should be equal to whatever this area under our curve is. But since we don't have a good way to find that area, the best thing we can do here is come up with a method to approximate the area under the curve. And the way that we're going to do that is we're going to divide our interval from 0 to 2 up into some subintervals. And we're going to draw some vertically oriented rectangles underneath it. Find the area of those rectangles, and then use that to approximate the area under the curve. Now, there's multiple ways we're going to do this. There's actually 3 different ways we're going to do that, and we'll look at all 3 of those in a second. But the general idea is we're going to draw, some rectangles in here, and they can be the same width, different widths. Right? Some of them might be bigger or smaller. Now, obviously, I'm going way over on some of these, and that's probably not the best plan. But I'm also going under on some of them, and so that's okay. This is just kind of the idea of what it's going to look like. But this isn't any of our specific methods. And if I know the width of each of these, if I said, okay, well, at 5 minutes in, right, where t would be 1/12 here, right, I know my width here is 1/12, and I know that I know that the velocity I'm looking at there is about 65. So if I did 65 times 1/12, I know that in this little section, I went 65/12 of a mile. And then I do the next one and say, oh, this one has got a different width, a little bit bigger width. It's higher up, it's about 70. So I do 70 miles an hour, the height, times whatever the width of that one was. And so, and of course, we could draw these rectangles as arbitrarily as we wanted to, but it's going to be a lot nicer and a lot easier for us if we do them in a uniform way. So the first way we're going to do that is with what's called a left rectangular approximation, which means we're going to take our interval from 0 to 2, and we're going to divide it up into, if we can, and usually we'll be able to, equal subintervals. And so you can see I've got 8 little subintervals down here, 0 to 1/4, 1/4 to a half to 3/4, 3/4 to 1, and so on, down to 2. So that I have a uniform width to each of these rectangles that I'm going to draw. And then, since this is going to be called a left approximation, a left rectangular approximation, or we'll call these left Riemann sums, we'll just make our rectangles starting with the left endpoint of each interval. And so I'm going to start at where my first interval has its left endpoint, that's at 0, go up to the function there, and then go straight horizontally across, and then drop it down there so that I've got a nice little rectangle that I know the height of, and I know the width of. And then we'll do that again at the next one. So here's my next interval right here. I'll look at the left endpoint of that, which is right here. And we'll go up until we hit the function right here. We'll go straight across and drop it down. And we'll just keep doing that. Again, the left endpoint of this interval, so that'll be at 1/2. We'll go up till we hit the function and go straight across and straight down. And we'll just keep doing that over and over and over again until we have made it to the end of our interval. And we'll, of course, note that some of the portions of this we're missing out on, right? We went a little under there, a little under there, underneath there, underneath there. But there's also some portions that we went a little over, a little over, a little over, and a little over. And so some of those are going to kind of cancel out with each other and get us a pretty decent approximation for the area underneath this curve. And one thing that we'll note here on a left rectangular approximation is that when my function was increasing right here, we'll note that our approximation was under the true value because our rectangle was underneath the curve. And anytime our function decreased, like right there, in that second interval, our approximation was an overestimate. And I'll have this written down on a slide in a little bit, and how we can determine whether it's an under and overestimate for any of the functions that we deal with based on whether they're increasing or decreasing. Okay, but when this one increases, the left is an underestimate, and when it decreases, a left is an overestimate. So now we're going to do the same thing with what's called a right Riemann style now. You can probably guess how we're going to do this. Exactly the same way as the left, except we're going to do it from the right. So I'm just going to start over at my last subinterval here, and I'm going to go to the right endpoint of it over at t equals 2. Go straight up until I hit my function, straight over, and then drop it straight down. And then I'll look at the next subinterval right here. I'll go to the right endpoint of it, go up to the function, straight across, and drop it down. And again, the right endpoint, straight across, and drop it down. Right endpoint, straight across, drop it down. And just keep repeating that process until I get to the end over here. And we can see that, again, we've got some sections that extend over. And we've also got some sections that went a bit under. And it looks like those are flipped this time. And so we could note that anytime my function increases, like on this first interval, our right rectangular approximation is an overestimate. And anytime our function decreases, like that second interval there, our right rectangular approximation is an underestimate. And again, I'll have that written down on the slide in just a minute. Now, the third way we're going to do this, which is actually going to be more accurate than either the left or the right approximation, is with what's called a midpoint approximation. So I'm going to give myself the same 8 subintervals here. But this time, as I draw my rectangles, I'm going to go to the midpoint of each subinterval. So if I'm looking at this first subinterval, the midpoint's right about there, right in the middle. I'm just going to go straight up here until I hit my function. I will draw a horizontal line that extends across that interval. It goes through the function at that point, and that'll be my first rectangle. And then I'll do the same here. I'll go up in the second interval from the midpoint and draw it straight down. And I'll do it again. Looks like the third one's right about here. The fourth one in the middle should be right about there. And we'll just keep going and doing these until we get over to the end of our last interval. And you can see with the parts that are extending over or going under are a lot smaller this time, which means this is going to be more accurate than our left or our right approximation. And we can see that when our function's increasing, like in this first interval, we have a section that we went a little over. We also have a section that we missed out on. So whether the function is increasing or decreasing isn't actually going to give us any information. What's actually going to give us the information about whether it's an over or an underestimate is the concavity. So if we look over here at the last one where our function is clearly concave down, that big chunk where it's concave down, we can see that we were over the function. And if we were to look at a portion that was significantly concave up, we'd see that we're getting an underestimate. So we don't have any that are like significantly concave up, but right here we can see that this little bit that we're missing out on is a little bit more probably than this little sliver over here. We're underestimating. We're missing more than we're overshooting on that place. So here are those rules on when it's an under and overestimate. Our left rectangular approximation is an underestimate when your function is strictly increasing on the interval, and it's an overestimate when it's strictly decreasing. And the opposite is true for the right. The right rectangular approximation is an underestimate when your function is decreasing, and it's an overestimate when your function is increasing. And the midpoint will underestimate when you have a function that's concave up, and it's going to overestimate when you have a function that is concave down on your x. So these are the basic ideas of our three different types of rectangular approximations. So we're going to just quickly go through and apply this to see if we can approximate the area underneath f of x equals x squared on the interval from 0 to 3. We're going to do it with a left, a right, and a midpoint approximation. And then we're going to determine if it's an under or an overestimate for each one. So here, the first one is 0 to 3, and it says 3 equal subintervals. So if we're doing 0 to 3 with 3 equal subintervals, we'll have 1 at 1, 1 at 2, and 1 at 3. 0 to 1, 1 to 2, and 2 to 3 will be our subintervals. And it says a left approximation. So we'll go into the left endpoint of the first subinterval, which is at 0. Go up to the function, which happens to be also at 0, and draw a horizontal line straight across. And so we'll see here that there's no actual rectangle. That's got a height of 0. So our first little rectangle gave us 0 times the width of 1. And then our second one, the left endpoint is at 1. We'll go up to the function and draw the rectangle. And the height of this was 1 unit, and the width of it was 1 unit. 1 times 1 is 1. So we've got 1 unit of area there, or 1 square unit of area. Then we'll do it for the last subinterval from 2 to 3. We'll go up till it hits the function. We'll go straight across and drop it down. And our area here is 4, a height of 4 times a width of 1. So 1 plus 4 plus 0 gives you 5 square units as an approximation for the area under the curve. And just by looking at it, we can see it's clearly an underestimate, but we know it's an underestimate anyway, because a left rectangular approximation will underestimate a curve when it, or the area under a curve when the function is increasing. And if we weren't sure what the actual true area of it was, we know at least that 5 is a lower bound of what that is. So now we're going to do this again with a right rectangular approximation. So 0 to 1, 1 to 2, and 2 to 3 again. But this time, we'll draw our first rectangle, starting with the right endpoint here at 3. We'll go up till it hits the function, straight across, and straight down. That's now got a height of 9. We know it's 9 because this is the function f of x equals x squared, and we went up from x equals 3. So this is 9 times 1. 1 for the width here. And then we're going to go from 1 to 2. We'll go up to where the function has a point at x equals 2. Make that rectangle, which is going to be 4 times 1. And then our last one will be at 1. We'll go up here and go straight down. That gives us 1 times 1. And so we end up with 14 as our estimate here. And just by looking at it, we can see that this is way over. We got all these chunks that are over, but we know it's an overestimate because this is a right Riemann approximation or right rectangular approximation on an increasing function. And we now know that a lower limit for what this true value might be is 5 from the left approximation, and an upper limit on what it might be is 14 from the right approximation. Now we should be able to get quite a bit closer by using a midpoint approximation. So this time, we're going to use the same interval, 0 to 1, 1 to 2, and 2 to 3, but instead of drawing our rectangles using the left or the right endpoints, we'll use the midpoint. So here at a half, I'll go up to the function, draw a line straight across, and get a very small rectangle there. And we need to now know what the height of that rectangle is. We know its width is 1, but its height is just the value of the function when x is a half. Well, that'd be 1/2 squared, since f of x is x squared. And the second one will go straight up from the middle of 1 to 2, which would be 3/2. And so this one should be a width of 1 times 3/2 squared. And then the last one is also going to have a width of 1. But this time we're going to go up from 5/2. And so it ought to be 1 times 5/2 squared. And so that ought to give us 1/4 plus 9/4 plus 25/4, which should be 35/4, or if you prefer, that's 8.75, which is actually pretty darn close to the true area. The true area under this curve, which we'll learn how to evaluate pretty soon in the next week or so, is actually 9 units. So 8.75 is a pretty good approximation. And now I told you the true area is 9, which means that this must have been an underestimate, but we have to determine why. And so we'll have to say, well, f prime of x is 2x, and f double prime of x is just 2. Since 2 is greater than 0, this function is concave up, which we could see, and we knew anyway. But a midpoint approximation, the midpoint rectangular approximation, is an underestimate because f of x is concave up. So now real quickly, we'll do one more example of a midpoint rectangular approximation, and then we'll be done for today. So we're going to take the function f of x equals 1 over x plus 1, and we're going to approximate the area under the curve on the interval 1 to 9 using 4 subintervals. So if I'm taking 1 to 9, which is 8 units long, and dividing that up into 4 subintervals that are equal, there'll be 2 units in length each, which means they're going to go from 1 to 3, 3 to 5, 5 to 7, and 7 to 9. And each of those are 2 units length. And we're using a midpoint approximation, which means we need to use the height of the function at x equals 2, at x equals 4, at x equals 6, and at x equals 8, at the midpoints of each of those subintervals. And we'll note that now the width of each of those rectangles are actually 2 units because we're going 1 to 3, 3 to 5, 5 to 7. So our first piece of this should be 2 for the width times the value of the function when x is 2. Well, that's 1 over 2 plus 1. And then the next rectangle will also have a width of 2, but it will be evaluated when x is 4, which will be 1/4 plus 1. The next one also has a width of 2, and then we'll evaluate the function at 6, 1/6 plus 1. And then the last one has a width of 2, and we'll evaluate the function at 8, 1/8 plus 1. And so it looks to me like if I were to distribute that 2 through each of these, this gives me a 1 plus a 2, which is 3. And then this 2 to this one, and this 2 to this one, and this 2 to this one is another 2, 4, 6. So it looks like I've got 9 there. Plus 2 times a fourth is a half. And then 2 times a sixth is a third. And 2 times an eighth is a fourth. 9 plus a half plus a third plus a fourth. Common denominator there is going to be 12. Looks like that's going to come out to be 6 twelfths plus 4 twelfths plus 3 twelfths. That's 13 twelfths plus 9. Well, looks like that's going to end up being 121 twelfths. And now we want to know, is this an underestimate or an overestimate? So the only way to figure that out is to find a second derivative, since this is a midpoint approximation. So f prime of x is the derivative of 1 over x. Remember that 1 over x is the same as x to the negative 1. So that'd just be negative x to the negative 2. And then the derivative of 1 is a constant, so it just pairs. And then our second derivative, we'll just use the power rule here. Negative 2 times negative 1 is positive 2, x to the negative 3, or 2 over x cubed. And we can see that the only place this thing might change concavity would be at x equals 0. And x equals 0 is not on our interval, so that means that this function is either always concave up or always concave down on our interval. All we have to do is evaluate it at any number between 1 and 9. So let's say f double prime of, I don't know, 2. What's f double prime of 2? Well, it's 2 over 2 cubed. That's 2/8. That's a positive number, which tells us this is concave up. And if we have a function that's concave up on an interval, then our midpoint rectangular approximation ought to be an underestimate. And that's going to do it for today. Next time, we're going to talk about one more method for approximating the area under a curve. And then we're going to take this idea of drawing rectangles underneath the curve and see if we can find a way to find an exact value for the area under a curve rather than just approximate. But for today, that's going to be it.